You've all heard all sorts of mention in the last couple of days, and you will continue to hear mention of this thing called the Birkeland current. And all of you, to a lesser or greater degree, have some idea about what is meant by that term. And what I'd like to do is to give you some results that I've developed over the last year to try to nail down some of the properties of Birkeland currents. There are some well-known properties of Birkeland currents that I think most of you will know in no particular order. The definition of it is it's the flow of electrical charge in space. So that means there is an electrical current, the flow of charge. How many coulombs pass an observation point in 1 second constitutes the amperage of that current. Currents create magnetic fields. In other words, if you have a Birkeland current, if you have a current, you will have a magnetic field. And if you have a magnetic field, you better remember that there's a current there that made it. Some astronomers lack that insight, I guess. These currents, one example of a Birkeland current is the one that connects the sun to the Earth, that powers up the aurora borealis, the aurora australis. And the man who discovered that fact was Christian Birkeland, after whom those flows are named. He was dogged for years by a man whose name was Sidney Chapman, an astronomer who claimed that Birkeland was crazy. Obviously, there could be no flow of current, of charge through space. It would all dissipate. At first, they said, well, space is an insulator, and you can't get current through an insulator. Then they changed their mind and said, oh, no, space is a perfect conductor. Well, you can't have it both ways. Actually, the latter is closer to the truth. Space contains plasma, and plasma is a very good, not perfect, but very good conductor. And so when charge flows in a plasma, it has certain properties. There's a picture of what those Birkeland currents look like. They come from the sun, and they drop down into that cone at the North Pole and the South Pole of the magnetosphere. Also, yes, the typical properties of Birkeland currents: they twist, they often come in pairs, they produce helical magnetic fields. We'll talk some about that. In fact, we'll talk a lot about that in the next half hour. Sometimes they're called vortices. They form filaments in sunspot penumbras. You've probably seen those. There's a picture of what they look like. On the right is a single Birkeland current. You can see the twist. The left-hand picture, when it's magnified, you can see they do very often come in pairs. They're very straight, typically. They can curve and twist too, but they are straight, and that's a mystery. If you have a fire hose and you spray a fire hose, if I had one in my hand, I don't think I could hit somebody sitting in the back row of the room. The thing would dissipate. These things, contrary to Sidney Chapman, do not dissipate. And the question is why? And I hope to answer that this morning. They connect stars and strings. Remember years ago, you probably heard astronomers, somebody would say, gee, it looks like those stars form in strings. The astronomer would say, no, that's an optical illusion. They don't form in strings. Yes, they do form in strings, and those strings are Birkeland currents. The Birkeland currents also connect galaxies. Just a couple of weeks ago, I think Walt mentioned this the other day, there was an announcement in Science Digest that astronomers, Australian astronomers, and some, I guess coupled with some here, have discovered that galaxies do indeed form on strings, which is a big reversal. Anyway, I developed over the last year a method for taking a close look at what the magnetic field is, what it looks like, the structure of it, around a Birkeland current. So if we just assume in your mind's eye for a second, in space, you've got this bunch of charges that are flowing along, what will happen? I've just said they will make a magnetic field, sure, but what will the shape of that field be? And what will the properties of that whole operation look like? I've discovered, and because of the results of this work, that the magnetic force fields that surround Birkeland currents reach out vastly, and I can't overemphasize that word too much, vastly farther than into space than previously thought. The magnetic fields that the Birkeland currents create wrap around them similar to the bindings of Roman fasts. You know, the fascist business, you can take a bunch of sticks and wrap it up, and it's much stronger with the wrapping than the individual sticks would be. I searched the internet for a picture of a Roman fast, and that's the best one I can come up with. Clearly, that winding, it goes around in one direction, but in reality, maybe not on that picture, it also wraps around going back from left to right and right to left. I'll talk more about that in a second. What is a minimum energy field? Somebody mentioned that the other day. In nature, stuff tends to seek a minimum energy. Water runs downhill. Perfume spreads out, will diffuse. If I uncorked a perfume bottle here, in a few minutes, the people in the back of the room would smell the perfume. People in the front row would smell it first. And after a while, if I left it open long enough, there would be a level concentration of perfume throughout the room. And so stuff just tends to shrink away. If you push on it, it'll move away to avoid the push. And it's a natural thing. Lightning follows whatever path seems to lead downward to a lower voltage. Planets, one of the primary, what should I say, claims of the electric universe is that the separation of the planets is due to a push back and forth, a jockeying. Many people don't realize that the planet Venus has a long tail, and that end of that tail, it carries electric charge, and that tail just flicks the outer regions of our magnetosphere as Venus passes between us and the sun. And if we get too close, our theory is there's a push. On Earth, electricity goes wherever you lead it. You push, you say the wire goes like that, that's the way the current's going to go. Provided, of course, you put a voltage at one end and a lower voltage at the other end so that that charge can flow downhill to a minimum energy. In space, however, it goes wherever it wants to because there are no wires. So that lightning, that charge moving through space, through, at least in this case, through our atmosphere, is following a path that it wants to get from a higher voltage to a lower voltage. Why doesn't it go in a straight line? Well, because it meets up with all sorts of stuff in the atmosphere. Little regions, clouds of charge, changes in humidity, maybe a cloud or something here or there. It is going as it senses downhill, just the way water would ripple down over the surface of a mountainside. And of course, if you really get out in space, it does go where it wants to, as long as you leave it alone. As long as you don't put any rocks in its path. As long as you don't put a magnetic field there so that it will disturb that direction of that flow. That's the jet from, what is it, M83, I think? 87. And that thing is over, several hundred light years long. And see how well it's collimated. It's a heck of a lot better than your garden hose. So the question is, why is it collimated? Why does it stick together like that? Well, there's one thing that even that jet from M87 senses, and that is the Lorentz force. There's a current there, right? And if there's a current, you know there's a magnetic field. Well, if a current crosses over a magnetic field, you get what's called the Lorentz force. This is as complicated as the talk gets, so don't sweat it. If you point your red arrow in the direction of the current flow, and it crosses a magnetic field, that's the direction of the blue arrow, and you point your fingers in the direction of the red arrow, and then move your fingers toward the direction of the blue arrow. In other words, start with the current, and then move toward the magnetic field. Your thumb is going to be in the direction of the force that those charges are going to experience. In other words, in this situation, the charge, which is flowing from left to right, will start to curve up. And that's how cyclotrons work. You know, the things go around in a circle. And the radius is called the Larmor radius. Well, anyway, that's the only force that charge moving in free space, if you leave it alone, will suffer. It'll feel that Lorentz force. I realized that, and I didn't invent that idea, I just realized it. And then I found in Tony Peratt's book an equation that says if you want to have a cosmic Birkeland current at a minimum energy, suffering no forces, the way to get the Lorentz force to zero is to have that Birkeland current look like this. And out comes this big equation. Now, if you're a mathematician, and I am surely not, then you can visualize what that structure has to be. Well, I looked at that equation for a long time. And as I say, this talk is a non-mathematical talk. But the actual, for those of you, I know it's Thunderbolts 1 and Thunderbolts 2. If you can go on the web, you can look at that site. That's my site, electric-cosmos.org/birkelandfields.pdf. Remember the capital B and the capital F. You can see the paper, and you can wallow around in the mathematics as much as you want to. What I did was, when I got that equation, I plugged it into a computer and did an iterative solution, almost exactly the same as Dr. Wolf was talking about in the generation of fractals. You get the equation, pick a number, stick it in, see what you get. Then take that number and stick it back in the equation and see what that produces. And eventually you get this trail. Well, I didn't generate anything as wild as a fractal, but I did come up with a solution. And I will show you the solution in a second. But that's the purpose, was to get an equation, the results of which would result in a Birkeland current that is free, left alone. Leave it on its own devices, what will it look like? To understand this, we have to talk a little bit about cylindrical coordinates. Is there anybody who doesn't have any idea what a cylindrical coordinate is? You know what Cartesian coordinates are, the x, y, and z in there. You see the x, y, and z? Z is the vertical axis, x is coming out at you, and y is going from left to right. You want to specify the position of a point like this guy up here. You can specify, well, it's this far in the x-axis, this far in the y-axis, and this far in the z-axis. Then that's the point. Cylindrical coordinates is the same thing, except instead of the x and y-axes, you still use the same z-axis. But instead of x and y, you replace x and y by at what angle are you from the center of this cylinder, from this pipe, let's say, and how far out are you? So that really, if you think about a Birkeland current, think about an oil pipeline or a water pipeline, it doesn't make any difference where Z is particularly, because it's all the same. The things don't change in a cylinder. It doesn't even depend on where you are in theta, because there's no, it's not asymmetrical, it's symmetrical. It doesn't make any difference whether you're at the 3 o'clock position, the 6 o'clock position, or where you are. Radius, oh yeah, that makes a big difference. How far you are out from the center of the thing is critical. So what my results were, it came up with, I'm trying to plot the magnitude and the direction of the magnetic field, and that's this B vector. And the B vector has two components. One in the direction of the flow, Z, and one in the wraparound direction, the theta direction. So if you can come up with a solution that will enable you to tell what BZ is and what B theta is, how strong they are, for any given radius you are out from the center of this thing, then you can predict and plot what the magnetic field is going to look like. Okay, now hold on to your seats, because there's the answer. And it may not make much sense looking at it, but let me see if I can explain what I'm talking about. The black line is the strength, it starts off there at 1, of the axial magnetic field, BZ. That's how strong the field is along the axis of the flow. The red component is the strength of the wraparound field. The horizontal axis here is not time, please, it's not time. It's the radius, the radial distance you are out from the center of this flow. So can you begin to see what's going to happen? right at 1 or at 0, as close to the axis here as we can, the vertical axis as we can get. The wraparound, the red, there is no wraparound field. It's all parallel. The magnetic field is exactly in the same direction as the current. And then as you begin to come away from, that is, increase the radius, that axial field component, and of course, the sum of the two vectors, bz and b theta, is the b that we're looking for. So what's the sum of two component vectors? Well, it's the square root of the sum of the squares, right? X squared plus y squared, that's z squared. Well, that's the light blue curve. So the light blue curve, the cyan curve, is the strength, total strength of the magnetic field as a function of how far you come out from the center of a Birkeland current. And other than maybe a couple of, you can see there's maybe a couple of little ripples in it here at the close in small values of r, it comes down pretty well decaying like any decaying exponential, right? Well, no, not like any decaying exponential. That, you see the purple curve is 1 over the square root of r. So most people, okay. If you know what we are so proud of in the electrical universe, and that is we're always saying to the astronomers, gravity goes down as 1 over r squared. And the magnetic field from a wire carrying a current goes down as only 1 over r. That's much less rapid decay. 1 over r is much less rapid than 1 over r squared. This goes down as 1 over the square root of r. So this stuff reaches out into space much farther than we had heretofore thought, because there are no wires up there. We don't get any 1 over r decay. We get a 1 over r, the square root of r decay, which means this stuff has a much wider effect than we had ever sensed before. Also, if you think about it, try to visualize in your mind's eye what's going to happen as you go out to higher values of r. First of all, the axial strength is getting weaker, and the red curve is building up to a maximum, and that maximum occurs almost, not during the first cycle, but the other cycles, it's almost exact. The maximum of the curlicue, kind of the curling around field, occurs when the axial field component is 0. So what that means is, just look at these 11 plots, just look at number 1. Think of yourself as you're above this Birkeland current. The Birkeland current is in the cylinder, and the cyan colored arrows are the direction of the field, the whole field, because there is no wraparound. And then if you come to plot number 2, that's a little farther away from the axis of the flow, and you begin to see that the curlicue, the curl around field, begins to contribute. The axial field gets weaker, and the whole thing begins to tilt. And so this magnetic field begins to wrap like a fask around the current. And then in step number 3, you see that even the wraparound field is stronger, yet the white arrows in each of these successive diagrams is simply the one, shows you the one before. And so each successive diagram is you're one layer higher away from the center of this flow. And the white field shows you what happened, what is happening just below the blue field. Eventually, when you get to, well, somewhere out here between 4 and 5, you can see that the white arrows are really 0. In other words, there is no axial magnetic field. It's all wraparound. It's just as though you took tape and just wrapped it around that pipe. And then as you go farther and farther away, the axial field actually reverses direction, begins to come back at you, and so the curl is down. And then finally, well, not finally, but when you get to, say, number 6, the axial field has reversed and is just against you. And 7, again, what's going on between 6 and 7? Well, in 6, there's still a very weak wraparound field. At 7, the wraparound field is 0. No, at 6, it's 0. At 7, it's beginning to wrap the other way. So first of all, it wraps that way, then it goes, and then back down that way. Perhaps some of you have seen that diagram. That was published by one of our EU heroes, Hannes Alfvén. And you can see that the red arrow is right near the center of the flow, and it's a very, what should I say, the pitch of it is not very high at all. Then the farther out you get, like you go to the blue arrow, then the pitch is less. It's a finer thread, if you will. And then finally out to the green arrow, well, that's out there somewhere between my diagram 3 and 4. The axial field is 0, and the thing just goes around. That's fine as it goes. As far as it goes, Alfvén was right. He just didn't go far enough. Because the next radius out, bigger than the green circles there, would produce something like the blue, except a wider radius, and instead of going up, it would come down. Let me sort of give you an analogy. The perfume bottle, when I opened it, would go to all corners of the room. It would spread out in all dimensions. And this is also a minimum energy field, and that means that this magnetic field is going to wrap around the current every possible way it can. And so it isn't just going to go clockwise and then stop. It's going to go clockwise and then counterclockwise and come back down again. So the question is, well, so what? Well, here's a comparison of the field strengths. The yellow curve is 1 over the square root of R. The purple curve is the wire's magnetic field, which is 1 over R. And if you look at a couple of different radial distances there, my observation number 2 says that the Birkeland current magnetic field is 32 times stronger than gravity at R equals 10. And it's even 3.2 times stronger than the previous EU estimate, which is due to the magnetic field in a wire. But there ain't no wires out there. So therefore, it spreads out even farther. The Lorentz force compresses matter at various radial fields. I don't know how much longer I got here, but let me just try to give you what I think is the most important thing. And that is, here's a picture. The circle thing looks like a bullseye. As you're looking down a Birkeland current, and if you pay attention to the thin little black circles, what you see there is, and you can, if you look at the numbers, the radius distances, which I've tried to list here, and compare them with what you see along there. For example, at 30-something, 31 here, and you look at 31 down here, that's a place where the axial strength is 0. And so what you've got is simply the wraparound current, the wraparound magnetic field, rather. The red is at a maximum, and so there's what I've tried to draw there at 31. You can see that's a strong wraparound current. If you come out to radius, 73, you can see that, again, you're at a point where, at 73, where the wraparound field is very strong, the axial field is 0, and so what you got is the thing goes around the other way. Okay, so what? Well, consider yourself as a positive charge, and you're heading down the highway here. And you are going to either intercept, depending on how far your path is, whether you're right at the center or whether you're a little bit farther out from the center of this flow, are you in the right-hand lane or the high-speed lane, you're going to encounter either this, at that point, downward magnetic field, or if you're out here, you'll encounter an upward magnetic field. You see it? Well, now think about the Lorentz force. If you're at radius 31, you're going that way. The magnetic field is down, and so you got a force pushing you in toward the center. Remember, the Lorentz is you put your fingers in the direction of the flow of current charge, then change them into the direction of the magnetic field. Your thumb tells you what the push is going to be. So you've got current going in at radius 31. You got the magnetic field downward. So in, down, the force is in. So any charge around the radius 31 is going to be squeezed into the middle. Is that good? Yeah, it's good. Because in the middle, you've got a very strong axial, the black line is at the maximum. You got a strong field going that way, and you have nothing that is in any other direction. And when the current wants to go in the same direction as the field, it's a superhighway. So that's why these Birkeland currents work so well right in that first little area. Well, what about the rest of it? Well, you can spend some time, doing this kind of stuff. But for example, at radius 75, look at 75. The Z field is 0, and you got a counter-rotating magnetic field. And so what happens? You're heading into the board, you're a plus charge, and you put your fingers in the direction of your flow, and then you look at the magnetic field, it's up. So okay, your fingers are there, go up, out. So any charge that's flowing around 73, radius 73, is going to be expelled outward from the flow. And so every time you come to one of these reversals, you get either you're going to be pushed in or out. And that's what I've done. I've tried to mark in the pink is where the charges end up. Okay? So clearly, hope it's clear, if you look at this long enough, it becomes clear, I guess, that in places like, pick anything, like pick 136 out here. There's a place where, what's going on? Well, at 136, you look along over here, someplace that's right there. That says that the wraparound field is 0 and the axial field is negative. So at 136, there is no wraparound field, it's 0, and this magnetic field is coming at you. Doesn't that defeat the purpose of this? Well, you don't want any current flowing back, you want current going that way. Well, you notice there are no charge carriers there. Because at 136, they're either pushed that way into this sort of first shell, or they're pushed outward to that shell. So regions like 51 and 136 radius, out here's another one, 220, it's sort of like a superhighway, but there's no cars on the highway. There's no charge carriers there. I hope I've shown that at certain places, certain radii, it's easy for current to flow, and other places it's hard for current to flow. And certainly because of the counter-rotating wraparound field, charges will tend to form in these layers. These layers are concentric cylinders. This is the same sort of result that Markland came up with Markland convection, if any of you are familiar with that. Markland, a Swedish scientist, engineer, I think, developed almost the same thing, except his mechanism is predicated on the idea that you've got a variety, a spectrum of different types of elements. And he found that what goes to the center are the easily ionizable elements. And to me, it's very counterintuitive. Iron and stuff like that are easy to ionize. So you'll find iron and the heavy elements in the middle. And one of the hardest elements of all, which seems absolutely nuts to me, but it is true, to ionize is hydrogen. And hydrogen is on the outside. So that's Markland convection. He's got the same result as this, that is, they're concentric cylinders, and there's a selectivity to what kind of elements you're going to find in which layer. And that's great. My result is independent of what you've got there. In other words, it doesn't make, this will happen no matter what the stuff is that's flowing. It could be just protons, it could be electrons. By the way, if all you have is electrons, just everything I said, just reverse it. It goes the other way. There's no problem. But the same kind of selectivity, the same kind of forming these concentric layers will occur. Well, is this true? Well, there's a famous picture of Saturn's North Pole. It's also the famous hexagon in the middle. You see the little one right in the middle. And my results here do not predict that hexagon. I wish they did, but they don't. But they do predict those circles. There's a Birkeland current coming down into Jupiter's North Pole. Same sort of thing. There are concentric circles, that's where the charge hits. That's where the charge is concentrated. And the wrapping around, by the way, I don't have any slide to show it, but the way this crazy going this way and then back that way, and then that way, it's wrapped like a Roman soldier. In World War I, the soldiers wore puttees, wrapped around their leg. I think they only wrapped them in one direction. But if you wrap them all the way down and then come wrapping them about the other way and then back down the other way, you got a real wrap. And that's a real reason, in my mind, that the whole thing hangs together and doesn't dissipate. There's a picture from Tony Peratt's lab. That's a dense plasma focus device. And you can see the circularity of it. You can almost, you can almost see this circle going one way and then going the other way. Here's a picture that C.J. Ransom and Mel Atchison can be proud of. They made that one in C.J.'s lab. And again, that's the result of a high amperage current. C.J., if he's here, he can tell you what the surface, the substrate is. But you can see it forms a bullseye. And the strongest one is, of course, that one right in the middle. So that's because of the properties, I think, we've identified here as the properties of a Birkeland current. We, Wall, me, a few other of us nuts, are convinced that what you're looking at there is a Birkeland current that's undergoing a Z-pinch. And you can see, I think very obviously, that the Birkeland current consists of concentric cylinders. You can see the outside two, certainly. And the center one, I think that and that are double layers in a central stream of current. And whether the current's going all one way or all the other, we've talked for hours on this and we still can't figure it out. But I would say, if that is indeed a Birkeland current, all the current's going one way on the outer sheath. Whether it goes in the opposite direction in the center, I don't know. But certainly it can go whichever way it wants to, because in the center, the magnetic field is lined up with the flow of charge, no matter which way it's going. And so it goes for free. It's a superhighway. Anyway, that's that planetary nebula M29. That's not Messier. It's, what was it? I forget. Somebody else quoted Walt Whitman, so I didn't want to be left in the lurch. And after all this lecture of numbers and all this, he says he looked up in perfect silence at the stars. You have to look. And I submit that's one of the primary rules of the electric universe, and that is, let your eyes tell you. And that is a concentrically made sheet of current. Again, just looking downstream, that's what you see in a Birkeland current. And there's that picture of Saturn. I submit that's pretty darn good evidence. Anyway, thanks.